So up to this point, we've been, whoa. We've been computing a lot of limits, and we've been talking about limits, and we've sort of used a pretty casual definition of the limit that is what the function wants to be as you get closer and closer to a specific location on the x-axis, even if it's not allowed to be that thing. Okay? And that has served us well enough up until this point, but it is important from the standpoint of having rigorous calculus foundation that we actually interact with the definition of a limit, which isn't all that different from our kind of casual definition, but there is a little more detail to it. And so we're just going to kind of do a little exploration today where we're going to look at the first limit that we ever considered, which was that rational function that ended up looking like a line with a hole in it. And we're going to see that our kind of intuitive understanding of the limit leads to this idea of the formal definition of limit. So we're going to look at a very specific case, that one, and then kind of go a little more generally to this is what it means to prove that a limit exists according to the very rigid formal definition. I'm just going to front load you that it can get a little tedious and some of the steps seem a little redundant, but I'm going to do my best to explain, like, here's why we do this part, and then we do this part. So bear with us. I'm not going to say it's not my favorite thing to teach. There's probably something I enjoy less, but it's not my favorite thing to teach because it is just a lot of notation, but I'm going to do my best to make it specific first so we can see it, and then more general. So we'll see. We didn't teach this last year because COVID. It's been a couple years since I taught it. Hopefully it's not too bumpy. Here we go. With that, the delta epsilon approach to limits. The delta epsilon approach to limits. We're going to go all the way back to 1.4 and recall that very first limit that we considered. So recall our first exploration of the limit. We looked at the following function. F of x equal to 2x squared plus x minus 3 over x minus 1. And we're going to go right ahead and factor this. And remember that this factor to 2x plus 3 times x minus 1 over x minus 1. And so what we were able to ascertain was that this is almost the linear function. I'm going to kind of lightly cross these out. This is almost the linear function 2x plus 3. It really behaves like it in almost every respect. The exception being at x equals 1, we don't have a function value. So because f was not defined at 1, what we did, we remembered that f is not defined at x equals 1. But we were able to use our calculators to get closer and closer and closer to 1 and see what our function was doing. Even though it was not defined, we used our calculators to find the function values as x got closer and closer to 1. So we're actually going to recreate that table now. Just going to spit the values out at you. Be a pretty big table. Got most of the rest of our page. Okay. And we have f of x equal to 2x squared plus x minus 3 divided by x minus 1. And so we started taking values kind of close to 1 from the left. I think we started at 0. And we found out the function had a value of 3 there. For 0.25, we were at 3.5. At 1/2, we were at 4. At 3/4, we were at 4.5. And then at 9/10, we hit 4.8. And we were off by 2/10, off of 5, basically. At 0.99, we hit 4.98, which we didn't really point out at the time, but we can point out now that was off by 2/100. At 0.999, we hit 4.998, which was off by 0.02. I think the last one we did was 0.9999, which spat out a function value of 4.9998, which is off by 2/10,000. Like we were getting pretty stinking close to 5. Kept getting closer and closer to 1. We could have kept getting as close as we wanted to 5. And that was kind of where we left our definition of the limit. But then we also saw, despite how close we can get to 5, if we try to plug in 1 here, there is definitively not a function value for 1. It does not exist. And then we looked from the other side, and we kind of had a mirror image that if we were within 1/10,000th of 1 on the right side, that spat out a function value of 5.0002. Check that out. That's the same distance away, off by 2/10,000ths, as it was when we were 1/10,000th away on the left side. And indeed, at 1.001, we have a function value of 5.002. We again see that match up with the corresponding input from the left side is off by 0.02. 1.01 gives us 5.02, off by 0.02, and then you kind of get the picture. At 1.1, we saw 5.2 as our function value. It was off by 0.2. So what the heck is going on here, other than rehashing stuff we've already seen? Well, what's going on here is that we can get as close as we could ever want to 5, so long as we are sufficiently close to 1. So if you spit out some very closeness to 5, like you want to be within 1/1,000,000th, there is a way to get our function to within 1/1,000,000th of 5, so long as we are close enough to 1. And it works on both sides. Okay, if we are 1/1,000,000th, right, here, if we were 1/110,000th smaller than 1, our function value was within 2/10,000ths of 5. But it also worked when we were 1/10,000th larger. Okay, so there's a wiggle room on both sides. So the way we're going to say this is that by choosing a value of x close enough to 1, we can obtain a value of f(x) as close to 5 as we please. And we did use some of this language a couple weeks ago when we were looking at this closer and closer method. I don't remember exactly how we said it, but it was pretty close to this. We can get as close to 5 as we want, so long as we are sufficiently close with x to 1. Well, now we're just going to dress this up a little bit and introduce these scary delta, epsilon Greek letters. They're not that scary, they're just letters. So we're going to translate what this means and what this means into a kind of more tight, coherent mathematical statement. But what this means, the left side, that choosing a value close enough to 1. If the absolute value of x minus 1 is less than some delta, this is the lowercase delta, then we obtain a value of f of x as close to 5 as we please, means the difference, or the absolute value of the difference, between our function value at that x and 5 is less than that desired closeness. And this letter here is the lowercase Greek letter epsilon. And so we can see this from our table, that let's say we want our function to be within 2/10ths of 5. We want our function to be within 2/10ths of 5. How close do we need x to be to 1? 1/10, because at 0.9 and anything closer to 1 than 0.9, or at 1.1 and anything closer to 1 than 1.1, the function values produced are within 2/10ths of 5. But notice what we did there, because this is like the critical hurdle that is going to trip us up if we don't see this. We chose the closeness to 5 that we wanted first. We said, hey, we want to be within 2/10ths of 5. And that determined what our delta was. So the epsilon determines your delta. Okay, you choose, hey, I want to be within this number of my limit. Then you go find the appropriate delta value based on that level of closeness you're looking for. But then the twist here is, once you've determined that delta, it is incumbent on you, and we'll see this when we finally get to the formal definition, to prove that, hey, yeah, if you have a delta and you have your x value less than that delta away from your 1 here, then you will always get function values within epsilon. Okay. And so we can see that, we kind of convince ourselves of that visually for this specific case. If you choose any value closer than 0.9 or 1.1, yeah, that works. But it's like this weird kind of game that we're going to play where we're going to choose our epsilon, see what the appropriate delta is, and then once we've seen what the delta is, go backwards kind of and show that, yeah, any delta or any function value, any x value that gives you a delta smaller than this will give you an appropriate epsilon. And if you're confused, that's okay. It's going to take some reps to kind of see how this works. So all we've done so far is basically formalize what we sort of intuitively had talked about already. We can get as close as we want to our limit, so long as our x value is sufficiently close to that point on the x-axis. Questions? So
I know, like you said, epsilon means like closeness, right? Like how close it is to our desired, like 5,
yep.
for example. So then delta, that's like the difference from the x value that would give us 5, or like.
Yes. So epsilon is the closeness to our output. The closeness to the function. Now, we're going to graphically look at this in just a second. Delta is the closeness to the x value that will produce that closeness to the function value. Okay. So I think a picture is going to do us maybe better than 1,000 words here. So what does this mean graphically? And this is where your rulers will come in handy. So graphically, we're going to use a full page here because no reason to try to squeeze this in. Squeeze. I'm going to use about 2/3 of the page on the graph. I'm going to set up my vertical axis. Horizontal. And we're going to plot the function we were just looking at. So this is going to be f of x is equal to 2x plus 3 times x minus 1 divided by x minus 1. Basically, we're just going to graph 2x plus 3 with a hole in it. So I'm going to use 2 lines on my paper for 1 on the y-axis. That's 1, 2, 3, 5, 6. I'm going to space out 1 a little bit so we have one more room. There's 1. So our function is going to look something like, remember there's an open circle at 1, 5 because there is no function value there. Draw in that line. And so we can see at 1, this function, it's like it wants to be 5, but it's never going to get there because can't plug in a 1 into this function. And so what the definition of a limit says is we can get as close as we want to 5 though. We're never gonna get there, we can close as we want. Actually, still some people drawing, so I'll stop talking for 30 seconds. Now, pay attention to the order that this is happening. We're never going to get to 5 because we can't plug in 1. However, if we want to get really close to 5, we can. At this point, we're just going to say within some arbitrary closeness. And we're going to call that arbitrary closeness epsilon. And so on my graph, and I would maybe recommend on your graph as well, I'm going to use 1 line away as our desired epsilon. That we want to be within 5 plus epsilon, or we want to be within 5 minus epsilon. Cool. Well, now let's see what this means for our inputs. This is where the ruler is important. I want you to take that ruler, and in this 5 minus epsilon, you're going to trace out a line until it hits our function. And then you're going to drop down vertically from that intersection. Yes, darker pen here. And then do the same with the 5 plus epsilon. Do the horizontal line until it intersects with your function. And then drop that down vertically. So we decided on an epsilon that was appropriate for us. We wanted it to be within 2/10, whatever it was. Epsilon can be anything. What is this distance from 1 to this dotted green line? That's your delta that corresponds with this specific epsilon. And visually what this means is, so this is 1 plus delta. This is 1 minus delta. If we are within this space around 1, less than 1 plus delta, or greater than 1 minus delta, if we're within a delta, this delta of 1, you can just, don't have to draw it out, but with your finger, let's say we're here. You go up on your curve. Is that within epsilon of 5? Yeah, okay, how about on the other side? If you're within 1 minus delta of 1 and you pick some x value to input, it goes up. And that's within epsilon of 5. As soon as you jump bigger than delta away, you don't have that guarantee. So if we're out here now, and we're looking at, let's do this in red maybe. This function value is not within delta of 5. Sorry, is not within epsilon of 5 because it was not within delta of 1. But again, the choice of epsilon determines the appropriate delta. Delta depends on epsilon, not the other way around. Okay. And so the way that we're going to say this, or I'll pause here. Does this picture make sense? Are there questions I can clarify? So we can squeeze this epsilon down as close as we want. And notice, and we can just picture this in our brain. What happens to delta as we squeeze epsilon closer? What would happen to this green vertical line as the horizontal lines squeeze closer to 5? They're also going to squeeze down. So the smaller you make epsilon, there's a corresponding shrinkage, a corresponding limiting of your delta values. Okay? So observe that this is what we just kind of said verbally, but we're going to write it down. That if x on the horizontal axis lies between 1 minus delta and 1 plus delta, then f of x on that vertical axis will lie between 5 minus epsilon and 5 plus epsilon. That's a lot of words. And as mathematicians, we like to be, if nothing else, concise, but not more concise than is appropriate. What did Einstein say? Make things as simple as possible, but not simpler. Okay. We aim to be concise here, but not more concise than is necessary. It's a lesson that some of us are still learning on our homeworks. But equivalently, we can turn this paragraph into a mathematical statement by saying, if the absolute value of x minus 1 is less than delta, if we are within delta in either direction of 1, then the absolute value of f of x minus 5 will be less than epsilon. We will be within epsilon in either direction of 5. And then there is an additional part to this inequality that seems a little unnecessary. They will always specify that this first part, the absolute value, needs to be greater than 0. And at first blush, you might kind of think, well, that kind of seems dumb, like it's absolute value. Of course, it's going to be positive. But what this guarantees is that x is never actually 1, because it can't be 1, at least here. So we need this restriction that this difference is greater than 0. It can get super, 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 super small, but it will never get to 0 because x will never get to 1. So the absolute value is less than delta, but it's also non-zero. Okay. And then kind of putting this back into some words, we can find, or we can make epsilon as small as we want, which has the result of f of x being as close to 5 as we want. By finding the small enough delta. Spell that word. And we're going to do this in red just to highlight the importance. epsilon is chosen first. In other words, delta depends on epsilon. The smaller we make epsilon, the smaller the delta becomes. Ooh, boy, oh boy. Good stuff. Okay, we're going to do one example with some specific numbers and values. And then probably take a quick smoke break, and then we'll attack actual proofs. Oh boy. So this last statement says we can make epsilon as small as we want, and therefore f of x as close to 5 as we want, by finding a small enough delta value. And so the question that comes up is, how small is small enough for a specific situation? And so our first example is going to look at that. And so the question that's bubbling in your brains, or that I'm telling you should be bubbling in your brains, is, so then, if we are given a specific epsilon value, how do we determine how small delta needs to be? What does a sufficiently small delta look like for a given epsilon? So example 1. We're going to look at how that can work. We're going to be given f equal to 4x minus 5. And since we're doing this after we've already looked at limits, let's just tell ourselves that we know, or think we know, that the limit of 4x minus 5 as x approaches 2, this is plug and play all day. 4 times 2 is 8. 8 minus 5 is 3. But let's say we're going to use this new kind of like sufficiently close to idea. So we know that the function is approaching 3 because, well, that's what it is. But suppose we wanted to be within a tenth, or no, I'm sorry, we're doing a tenth? Yeah, a tenth. So suppose, no, not red. We want epsilon within a tenth. What value of delta greater than 0, it's always got to be greater than 0, is sufficient such that if we are within this delta of 2, then we are within epsilon of 3. If we're closer to 2 than delta, then we are closer than epsilon to 3. And we're specifying that this epsilon, for this case, is equal to 1/10. So what value is going to guarantee we're within a tenth? Notice here, and we'll pull this out in the formal definition. What do 2 and 3 correspond to within the structure of our limit? Yep, and I guess I should say more generally, we have, what do we call this value that we're approaching? Remember what letter we would use? Yeah, this is our A value. And 3 is our limit. Okay, so let's kind of plot this out. It doesn't need to be super exact, but just to get a sense of what's happening here. Doesn't need to be that big either, but something like that. Call this 3. Call this 2. I don't even really care about the accuracy of the curve. Let's just put 2, 3 is on our graph. Looks pretty steep, actually. Not in this case, because this is just straight up a linear function. Okay, so I'm not really concerning too much about the accuracy of the slope here. What I do want to point out is what we're being told is we want to be within 1/10 of 3, meaning, of course, this is not to scale, 3.1 or 2.9. Everybody comfortable with where 3.1 and 2.9 are coming from? Those are the values within 1/10 of our limit. What we just did on this previous page was we said, okay, well, that corresponds to 2 specific delta values. Ooh, it's going to be pretty snug. That's okay. I screwed this up so royally. I guess I'm just not, oh yeah, that should be way closer to this. 2 is really like right here. Here's 3, and once at 2, our function has a value of 3. So we are in search of delta. What is this x sub 2 and x sub 1? So these are locations on your x-axis that need to be within delta of 2. And we could actually plot this curve on our graphic calculator and then plot the horizontal lines, y equals 2.9, y equals 3.1. Use our trace function, see where those horizontal lines intersect our curve, and the x coordinates of those intersection points would correspond with this x sub 1 and x sub 2. And that would be one way to do it. But we're going to do it analytically, just with our knowledge of algebra. This x sub 1 corresponds to a function value of 2.9. So we're going to write that out. That f of x sub 1, this guy here, is 2.9. And then in a minute, we're going to go through and do f of x sub 2 is 3.1. And from these two equations, we should be able to determine the values of x sub 1 and x sub 2, and then use them to determine our delta value. So if f of x sub 1 is 2.9, that means that 4 times x sub 1 minus 5 is equal to 2.9, using my function. Well, then that means that 4 times x sub 1 is equal to 7.9. Then we bust out our calculators. 7.9 divided by 4, 1.975. And then in a very similar fashion, on the right side, we can find our x sub 2 value. Because f of x sub 2 means 4 times x sub 2 minus 5 is equal to 3.1. Mean 4 times x sub 2 is equal to 8.1. 8.1 divided by 4, 2.025. Okay, so we just did some basic algebra, but what do these x values mean? We've figured out that x sub 1 is 1.975, x sub 2 is 2.025. Are these our delta values? Annette,
Delta 0.05,
how'd you get that?
the 2 minus either x sub 1 or x sub 2.
So the difference between these x sub 1s and x sub 2 and 2 is our delta. If we are between 1.975 and 2.025 on the x-axis, and we'll test a couple points just to like kind of verify, that will produce a function value that is within 1/10 of 3. The way we can show that is, again, we want the absolute value of x minus 2 to be less than delta. So the absolute value of x sub 1 minus 2 is 1.975 minus 2, negative 0.025 or 0.025. Over here, we see the same thing. Sure. So the difference here is what we're after. And we get a similar one over here. The difference between x sub 2 and 2 is the difference between 2.025 and 2. This turns out to be positive inside the absolute value. We end up with 0.025 in both cases. This is our delta. If we are 0.025 away or closer from 2, we will be 1/10 or closer to 3. So then, before we take our quick break, let's just like see that this is actually true. We've kind of done some analytical stuff. Just test a few points. that satisfy x minus 2 is less than 0.025, and verify that the resulting f of x minus 3 is less than 1/10. So somebody give me an x value that is within 0.025 of 2.
0.01.
X equals 2. Yeah, 2.01. And then f of x is equal to 4 times 2.01 minus 5 to 8.04 minus 5, which is 0.04. Is 4/100 less than 1/10? Sure is. Thank you. 3.04. I jumped ahead. But 3.04 minus 3 is what? 0.04, which is less than that 1/10. How about, let's get a little closer to 4. How about x is equal to 1.98. So f of x then is equal to 4 times 1.98 minus 5, which is 2.92. 2.92, the absolute value of it, minus 3 is 0.08, which is less than 0.1. So we could do this forever. We could just keep picking x values that satisfy this inequality and keep verifying that the resulting function value is within 1/10 of 3. And so this feels like a good delta for this epsilon. Again, this delta depended upon the choice of epsilon. We want to be within 1/10 of our function, or of 3. We need our inputs to be within 0.025 of x. I got 9:18. At 9:23, we will turn this into kind of our first semi-proof. Smoke them if you got them. You're not going to get through all this, that's for sure. break over. Nope. Put the phones away. Let's go. Let's go. Let's go. Don't start a class you don't know you can finish. Possibly. Yeah, I think what we're gonna do, we're gonna do one more example where we're gonna continue to look at the same function we just did, but now we're gonna put it into a little bit of more of like a proofy format. It's still not a formal proof because we still haven't seen the formal definition of the limit. But this will kind of be like the training wheels that allows us on Monday to do our first formal limit proof. And this is where we're going to kind of introduce a process that seems a little redundant, where we're going to find a delta value based on an epsilon. And then once we find that delta, show that we get back that epsilon. So like kind of seems like doing double the work that is necessary, but it will hopefully make sense when we see the definition. So example 2, we're going to call this the sort of proof. Sort of proof. Because this is really just an n equals 1. This is just a specific epsilon and finding a specific delta. When we prove it, we're going to show for any epsilon that a sufficient delta can be found. Have we seen this phrase or this idea of n equals 1 before? Where like somebody offers you proof of something based on their personal experience. Like, well, this happened for me. Well, it's like, yeah, it happening one time for one person in the history of humanity isn't like the greatest proof. That is one case that something happened. Okay, so this is going to be one case where we are able to find a sufficient delta given a specific epsilon. The proof writ large, the actual proof will be, here's an arbitrary epsilon, show me that you can find an appropriate delta. And that's what we'll do on Monday. We're going to see it with numbers first, because I think it makes a little more sense. So we're going to confirm analytically that delta equal to 0.025 is an appropriate choice for f of x equal to 4x minus 5 with a choice of epsilon of 1/10. In other words, we're going to show that if we want to find a delta greater than 0 such that when the difference between x and some number on our x-axis, which we'll call a, is less than that delta, then that guarantees that the distance or difference between the function value produced at that x and some number L, which we know is the limit, will be less than that epsilon. This is actually the formal definition of the limit. We're just going to do it with a specific. Well, the specific one that we're looking at right here is that we want x to be sufficiently close to 2 so that our function values that spit out are within 1/10 of 3. So we're going to verify that 0.025 is an appropriate choice and then show that, yeah, if you have it within that 0.025, you'll always be within 0.1. And so we do some kind of, seems like trickeration, seems like, I don't know, deconstruction. But as we do a couple of these, I think you'll kind of get the feel of it. So we're going to say, we're going to focus on this right part. Because again, epsilon is going to determine delta. And I know that is kind of confusing because it like reads left to right. And it seems like, well, delta comes first. Epsilon determines delta. And so we need to figure out if we want this to be less than 1/10, what does that mean for this inequality? And so we're going to kind of magically produce an inequality involving x minus 2 out of this inequality. It's going to seem like magic. It's going to seem like, why does that work? But then you're just going to see that it kind of has to work. And so what we're going to do is we're going to replace f of x with what the function is, which is 4x minus 5. It's replaced f of x, 4x minus 5, minus 3 is less than 1/10. Well, let's combine some like terms. Oh, keep skipping lines. I think it makes it a little easier to follow. 4x minus 8 needs to be less than 1/10. There should be guns here. Sorry about that. Then and then this is the part that you're not going to like for sure. But I will try to kind of convince you of it. If the absolute value of 4x minus 8 is less than 0.01, and you're not going to like this, then that also means that 4 times the absolute value of x minus 2 is less than 1/10. And I know your entire mathematical career, we told you the absolute value is like a prison bar. Like you can't do it, you can't go in, you can't go out, you're locked in the absolute value. You can factor positive numbers out of absolute values and not change the expression. And that might not feel super good. And so we'll do like a very quick, this isn't even a proof, this is just like, does this actually work off to the side? Because that should, does that bother anybody that I've just kind of undone 12 years of your mathematical life? Or are you guys just okay with that? You just accept that? Oh, all right, cool. Never mind then. That's true. Okay. It should kind of bother you. I mean, it bothered me when I saw it. Because remember in algebra 1 when you tried to distribute into absolute value and they were like, no, you're dumb. You could have done that as long as it was a positive number. Anyway. All right, we're just gonna accept that. You guys are either not caring or a trusting bunch. So now look at this. I said we wanted to produce an inequality that involved x minus 2, or the absolute value of x minus 2. Look what we just got. An inequality that involves the absolute value of x minus 2. So we're almost there. If this is true, then dividing both sides by 4, we have the absolute value of x minus 2 must be less than 1/10 divided by 4, which, oh, by the way, is 0.025. And so it appears that we have indeed confirmed that a choice of delta of 0.025 is appropriate. Now, this is half of the work. And what we need to now do is what I sort of tried to hint at when we were looking at the specific numbers. Where did that go? We did this. Like, this is just the formal version of our analytical work here. We said, oh, okay, it looks like 0.025 is appropriate. Epsilon determined delta. And then we just like picked a couple numbers to say, yeah, that actually seems to work out. That anytime we pick an x value that is within delta of 2, it appears to deliver a function value that is within 1/10 of 3. But we did it just like for two numbers. There's a lot more than two numbers in between 1.975 and 2.025. And so what we're going to do is, and this is where it seems maybe a little redundant, but it's the other direction of this to show that this actually works for every time. Is we're going to say, all right, if we've got this delta less than 0.025, then no matter what, we're going to get our function within 0.1 of 3. And so the second half of this is going the reverse direction. So because if delta is equal to 0.025, then what that means from our statement up here is that x minus 2 is going to be less than delta, or rather the absolute value of x minus 2 is less than 0.025. It's also got to be greater than 0. Let's not forget that. And so top half of the page, we were starting here and wanted to end up with something that involved the absolute value of x minus 2. Now we're going reverse. We want to show, okay, if we have this thing true, then we end up with this truth. And so we're going to do some kind of backwards finagling. Let's multiply both sides by 4. Actually, let's skip lines here. So 4 times the absolute value of x minus 2 is less than or equal to 4 times 0.025. In the same way that you guys were fine with us factoring out this 4, it is also legal to go reverse and multiply that in. We get the absolute value of 4x minus 8 is less than 1/10. And this part, we already know where we're going, so this goes pretty smooth. We separate this -8 into a -5 and a -3, still less than 0.1. Well, 4x minus 5 is, of course, f of x. So then this means that f of x minus 3 will be less than 1/10, which is what we wanted to show. So this is the part that seems like, well, why do we just have to show that if we just went the other way? Because once we've chosen that appropriate value, we need to guarantee that the forward direction is satisfied. And the forward direction says, if your x value is within delta, your function value will be within epsilon. And so we've now confirmed that. And so what we will do on Monday is we're going to do this, and I think we're going to use this exact same function. But instead of saying, hey, we want to be within 0.1 of 3, we're going to just use epsilon as a general placeholder. Say, hey, if I give you any epsilon, is there an appropriate delta that will get me to within that epsilon? And if we can show that, which we will be able to, then we will have proven that the limit of this function is 3. And that's the formal definition. Do you maybe appreciate that we didn't do this earlier? That even right now, I've spent 3 weeks doing limits, you're probably a little bit like, yeah, I kind of see it. But if we had seen this before we ever computed limits, do you think you probably would have been like even more lost? Hopefully, yes.
What's the purpose of like doing this part?
Just mathematical rigor and the fact that for the 250 years that they're talking about. That's not even true. Newton didn't do this. This is like a pretty new, probably within the 19th century, 20th century rather. They started to do these, and it's been a part of the Baptist tradition. And sometimes we interact with formal definitions of things. But it's important to know formal definitions, even if on a day-to-day basis, you know the definition of a lot of words, but like, you don't use all of them. You don't use these formal definitions all that much. But there is some academic. In the past, we made you memorize verbatim the delta epsilon definition of a limit. I had to do that 15 years ago. That was done. I don't know now. I can tell you what a limit is, but I can't tell you the verbatim white hole definition. Rigor within reason. I think that's a good policy. I got 939. I think what I would like is to assign you, or not that I'm going to sign off on Monday, because I think we'll need every minute that we can get on Monday. But if you are hankering for some math to do over the weekend, there is some stuff we can do. This will actually be back in 1.4, and this will eventually be due, so not like oh, sorry, it's not necessarily going to be Monday. Yes, I'm still recording. All of you. Oh, we need to get to the bottom of something.